Okay, cool. So in the last class we looked at quantization and we saw that although quantization is in principle a non-linear operation, we modeled it as some additive error that is getting added to our input signal like this. Y is the input, V is the output, and the error is the quantization noise or the quantization error. We made some observations on this. Firstly, we saw that as long as the input to the quantizer is within the full scale range, what can you say about the range this quantization error takes? Range of error. So this was taking minus delta by 2 to plus delta by 2, where delta is the quantization step size. And then we made a few assumptions on the quantization noise. One is that we treated this as a random signal. Then we assumed that it had a uniform probability density function, right? And from the PDF we calculated what is the mean squared value. Mean squared value, remember, is the power in the signal. Yeah, and this we calculated it to be delta square by 2. And based on this, we decided to quantify or form a metric to quantize, to characterize the performance of the ADC. So, which was the signal to quantization noise ratio. And in particular, we calculated the peak sinusoidal signal to quantization noise ratio. And in terms of the number of bits in decibels, how much was this?
6.02.
Yeah, 6n plus 1.76 decibels, where n is the number of bits with which you quantize, right? And from this we also defined enob, or the effective number of bits that your ADC is capable of digitizing the signal to. So that is the measured peak SQNR minus 1.76, so many bits. And then we saw to measure this enob, we will have to feed in a sinusoidal signal to my ADC. A sinusoidal signal is the maximum amplitude because we are interested in the maximum SQNR. And here in time domain we get some quantized waveform like this. Then we noted that from time domain it is not possible for us to distinguish signal from noise. So we have to resort to frequency domain, and that led us to the path towards power spectral density. So again, if you define it, the power spectral density for discrete time is defined as the expected value of magnitude squared of the Fourier transform scaled by n. And remember that this is a density function, meaning it gives you the power around a particular frequency in a unit bandwidth, right? And if this gives the power in a unit bandwidth, to find the total power, what do? We integrate it, and this is a discrete time, this one. So no, it's a discrete time thing, but remember omega is still continuous. So what is the range of values with which I integrate it? Yeah, it's any interval of 2 pi, or if it's a single sided power spectral density, you would call it from 0 to pi. So let's say it's sorry, I messed up this. This should be x, because x. So this is basically sxx of e power j omega d omega, and whenever you have omega as the variable, you have the scaling factor of 1 by 2 pi. And this is one sided. So then we made an assumption that our quantization noise has a wide power spectral density. That is, its power spectral density is flat, right? Cool. But then we saw that although this is nice, there is a practical difficulty in measuring Fourier transform, the discrete time Fourier transform, which is this. So if you take the conventional expression, so we have summation running from 0 to infinity, x of n e power minus j omega n. So two issues. One is the fact that this variable omega is continuous in a range 0 to 2 pi. Second is the fact that the summation has to run till infinity. So the first problem, the fix was simple. You save or compute the spectrum at only discrete frequency points. So if you decide to take n points, so this interval of 0 to 2 pi is divided into n points. So you computed discrete frequencies like this, and these are called as frequency bins. And what is this bin width? 2 pi by n. Fine. So you compute the spectrum at multiples of 2 pi by n like this. And of course, instead of running the summation till infinity, you decide that you take the summation for finite number of samples. So that means we'll have a finite record length nr. But then we also observe that here, when we are computing the spectrum at discrete frequency points, essentially we are sampling in the frequency domain, which means if I reconstruct the time domain sequence from this, what do I observe? Sampling in any domain will result in a periodic repetition in the other dual domain. So this, when you reconstruct the sequence from this spectrum, you observe a periodicity, and from that argument it made sense that the logical choice is to choose my record length to be same as the number of frequency points at which you compute the spectrum, and this is called the n-point discrete Fourier transform.
So if you take record length to be less than n, then it would be like it would repeat after nr only, right?
Correct. No, it will repeat with this periodicity. I mean, basically, see, remember, the periodicity depends at the rate at which you sample, right? Here it is this n that determines the rate at which you are sampling.
Okay, it will go till the record length, and then it will drop down
to 0.
Then.
Yeah.
That's one more question. Like fundamentally, what is the difference between quantization error and loss?
I mean, quantization error is called quantization noise. Both are same. Okay.
But since we are like defining quantization noise from statistical measures and error algebraically, so like.
Well, I mean, the thing is, algebra, I mean, statistical thing, both are same mathematically, right? Basically, the thing is, it is, yeah, the idea is it is this guy. Now, what we are saying is this variable, we treat it as a random signal and go ahead, that's it. So, don't confuse too much. Okay. So, yeah, so this gives the endpoint DFT, and so now if you actually define the power spectral density like this, SPV of k is 1 by n times expected value of magnitude squared of the discrete Fourier transform. Okay. So earlier we computed the power from the power spectral density like this, right? So let me copy that here. I put it here. So now I no longer have the spectrum for all omega, I have at discrete points. So if I were to compute the total power in the signal, how does this expression modify to?
Summation.
Yeah, I'll have 1 by 2 pi, nothing changed to 2 pi. Here I'm integrating with respect to omega, but we no longer have omega. You only have k as the variable, so that's a discrete variable k. And remember, here omega goes from 0 to pi. So k should go from what value to what value? 0 to n by 2. Remember, 0 to 2 pi is mapped as 0 to n. So pi maps to n by 2. And is xx of k. Okay. I mean, see, that's the issue with continuous to discrete. Basically, see, we include till pi. Pi is n by 2 exactly. Right? Idea is, if you have large enough n, whether you sum it till n by 2 or n by 2 minus 1, not make a lot of difference. But in principle, it is still n by 2. Okay. So SPV, so Sxx of k times you have d omega. What is d omega here? 2 pi by n. Fine. So that basically cancels this 2 pi here. You end up with. So that's how you compute the power. from the discrete power spectral density like this. Fine. So you sum up all the bins and scale it by 1 by n. That gives the total power. Okay. So which means now if I go and try to measure the enob for my ADC, I do the same thing as before. I feed in a sinusoidal signal with the maximum amplitude. I get some, say this is y. I get a quantized sinusoid V. You go and compute the power spectral density using the discrete Fourier transform like this. It's 1 by n, expected value of magnitude squared of the discrete Fourier transform. So if I plot the one-sided PSD like this, so this is SVV of k, I'll have k here. My k will go from 0 to n by 2. So I have a sinusoid. What do I expect the sinusoid to map in the spectrum? We expect that, we expect at least there should be one impulse corresponding to the input sinusoid. Let us say that is in the mth frequency bin, and rest all will be the quantization noise. This is what we expect the spectrum should be. Fine. So from here it is apparent, this is the signal, the rest is noise. Now you can distinguish the two and find both their powers separately. So how do you find the signal power now? Yeah, power at that point, but remember that when you are calculating the power, we are adding up the relevant frequency bins and scaling it by n. Okay. So here also the signal is occupying the mth bin. Yeah, so the signal power is dependent on the strength of this bin, but the actual, to be exact, it is 1 by n times the SVV of m. Okay, fine. And now we have to find the noise power. So what do you do? Yeah, I mean, one thing is you take the total sum, subtract the thing. That basically is the same thing as saying I am summing up all these guys except this, right? Again, see, in principle, even quantization noise also occupies the mth bin, but here the signal is dominating that bin, so you don't consider it. So strictly speaking, it is not accurate, but as long as you have large enough n, just excluding one bin here will not make a difference. Okay. So here if I find the quantization noise power, I will do the same thing, scale it by n. I will sum it for all bins except for the bin at which the signal is dominating. So once you have the two, you can take the ratio and then find the signal to quantization noise ratio and back calculate your enob. Okay. So again, see here, when you take the ratio, the scaling factor kind of cancels away, right? So with respect to SNR calculations, it is okay even if you don't consider the scaling factors, right? So that's why typically, loosely speaking, people will say that this will give the signal power, some of this will give the noise power. This is okay as long as you're interested in the ratios of the two, but if you're interested in the absolute value, you should be including all the scaling factors appropriately. Cool. So from our understanding, we expect that this should be the spectrum, but let us see if that is indeed the case, because we know that for a sinusoid like this, which is going from minus infinity to infinity, the discrete time Fourier transform will have an impulse like this in omega axis. But when you are trying to find the DFT, we are essentially truncating the signal for finite number of samples and then finding the spectrum of the truncated sequence, right? So let us see if that will also map like this as we expect. So for that, let's look at what happens when I take DFT for a sinusoid. So I'll start with a continuous time signal like this. Yes.
We are taking the DFT of the output signal, right?
Correct.
We are taking the DFT of the input signal.
No. We are taking the output of the, DFT of the output sequence only. But what I'm saying is now we'll consider a sampled sequence theoretically and see what happens if I take the DFT for that sinusoid. Okay. Basically, my ADC output contains sampled sinusoid as well as the quantization error, if I were to say it that way. Let's look at both of them separately and see. It's a thought experiment. Okay. So the idea is I'm taking the sinusoid, let us say cos 2 pi f naught t. I sample at a sampling rate fs. What is the discrete time sinusoid I get? Yeah, cos 2 pi f naught into n by. Okay. So I'll call this as my discrete frequency omega naught. So now we are trying to find the discrete Fourier transform of this discrete time sequence. That's what we are trying to do. So we have DFT when you are finding. Remember, when we are finding DFT, two things happen. One, we computed discrete frequency points. Second, we truncate this fellow to finite number of time points. So the truncation, as we saw, let me remark it here. When I take DFT, it's essentially I am taking a sequence x of n that can run from 0 to infinity. I truncate it for n samples by multiplying with a rectangular window. So this truncated sequence is what I work with. I find the Fourier transform at k times 2 pi by n. That's what is happening. So we'll try to do the same thing for the sinusoid also. Yeah, so this is my cos omega naught n. I multiply with this rectangular window. I'll just draw its sequence directly. So it's basically contains total of n ones and all the other samples are all 0. Fine. Like this. So this is the truncated sequence, and then you find the Fourier transform at. That's what you're supposed to do. So tell me, what will be the discrete time Fourier transform for a sinusoid like this? What do you expect? Just to expect two impulses at what frequencies in omega axis? Huh? Omega naught? I mean, it's a sinusoid with a frequency omega naught. If I plot its Fourier transform, discrete time Fourier transform, let us say, at what all frequencies I'll observe the impulse? Yeah, I'll get one at omega naught. Where else? Minus omega naught. Okay. I can say this is any 2 pi, in minus pi to pi, this will be the case, right? I look at an interval of minus pi to pi or 0 to 2 pi. So let us say now I look at only the positive side, right? Instead of looking at negative also, I say I look at only from 0 to 2 pi. Okay, so let's say, so I'll have one impulse at omega naught. So where will the other impulse now lie at? 2 pi minus omega naught. Remember that discrete spectrum is periodic with 2 pi. So this guy keeps repeating. So this, when you shift it with 2 pi, it will land at 2 pi minus omega naught.
In the previous slide, we have multiplied DFT into the rectangular window.
No, we are truncating the sequence, right? Truncating the sequence is multiplication with rectangular window.
Okay,
and the Fourier transform of the truncated sequence is what we are doing, right? So let me actually rewrite this. I'll just say that this is 0 omega naught. Fine. Let's do it like this. Is okay? Minus omega naught, if I look at the positive side, is 2 pi minus omega naught. That's all. So what is the spectrum of this fellow? It's a rectangular pulse. In time domain, if it's a pulse, what do you expect in frequency domain? Yeah, some sync. Discrete time, the sync is slightly different, but it's okay. If I sketch it, so let's say this is 0, I'll have something like this. Magnitude if I plot, it will look like this. Something. And what do you think are these points? What is this null frequency? 2 pi by n, pi by n. Huh? Why not pi by n? Can you disprove me? Okay, I mean, think about it. I mean, let's say I don't even know that the spectrum of this looks like a sink. Can you say that the Fourier transform of this sequence will be 0 at some specific frequency points? It's a simple math question. See, what do you do in Fourier transform? When you compute Fourier transform, what do you do? Huh? I mean, in slightly more mathematically, what do you do? Yeah, you multiply the sequence with sinusoids of different frequencies and take the integration or summation in discrete time, right? So here when you are multiplying a sinusoid with this sequence, that's going to truncate the sinusoid, right? So essentially you are looking at a sinusoid with n samples long, right? And when I integrate it, it should become 0, or sum it should become 0. So let's say this is a sinusoid. I am drawing continuous time for the simplicity. So how long do you think I should integrate the sinusoid so that the integration becomes 0? At exactly 1 clock cycle. So here my sinusoid lasts for n samples. So I should be looking at those sinusoids which when summed up for n samples completes, which when after n samples completes 1 cycle. So what is the frequency which completes 1 cycle in n samples? 2 pi by n. 2 pi is marking the end of one oscillation or one cycle. So this will be 2 pi by n. Of course, you can also have two integers, I mean 2 cycles, so that will be 4 pi by n. Is that okay? I mean, from this now you should be 10. Let's say you have a continuous time pulse like this from minus t to plus t. Where will be the nulls in the frequency domain? I mean, just as an extension, if I have a continuous time signal like this, where will the frequency nulls lie in the spectrum? 2 pi by 2t. Should complete 1 cycle in this window of 2t samples. So you don't have to remember, just this logic you should be able to say, right? There are some things that are worth remembering, some things which are worth calculating quickly. This is the second category. So anyways, so this is what happens. So now I'm multiplying this sequence in time domain. So this gets convolved. So what happens when I convolve these two fellows?
The sink repeats.
This guy will repeat around these two frequencies. So let me actually draw it separately. Take a long frequency axis. So let us say this is omega naught. It's going to shift around omega naught. Also around 2 pi minus omega naught. I will not draw that for simplicity. So what will be this null frequency now?
Omega plus
2 pi. So this is the discrete time Fourier transform, and you are going to take the samples at k times 2 pi by n, right? This is the spectrum of the truncated sequence, and I am looking at the spectrum at k times 2 pi by n. That is what DFT is doing. It truncates the sequence and looks at the spectrum of the truncated sequence at these frequency points. This is the spectrum of the truncated sequence. I look at these spectrum values at these frequency points. Okay. So let us say now I consider a case where omega naught is of the form m times 2 pi by n. Okay. It's an example. So this becomes m times 2 pi by n. This null becomes, what is the value of the null now? M plus 1 times 2 pi by n. This will be m minus 1 times 2 pi by n, and so on.
Why did you choose that n?
No, I'm just taking an example, right? Let's see. I mean, there are two possibilities. Either the frequency is of this form or it is not. We'll look at both cases. That's all. So now if I take the samples of this spectrum at these frequencies, what all points I will sample? I'll first, let's look at this portion. Where will I sample in this region? At exactly this omega naught, middle of that lobe is where I'll sample. The next sample will be what? Yeah, it will all be exactly 0. not to the left, not to the right, on the dot exactly will sample. Similarly, we'll have something here. So this will be what frequency now?
N minus n.
Yeah, 2 pi, something like this. So this will be n minus m times 2 pi by n. Similarly, we'll sample, you'll have this lobe here, you'll basically sample this fellow, and all the others will be 0. So essentially now if I look at the sampled spectrum, which is the discrete Fourier transform, in the k-axis, at what all frequency bins I will look at the, I will get non-zero values.
M and n minus.
I'll get at m and n minus m. Right? So you get two peaks like this. That's what you expect ideally. And all of them will be, all the rest of the samples will be 0. That's exactly what you would want. So this condition is typically called as signal lying on a bin. Again, for obvious reasons, my signal frequency is chosen so that it is exactly lying on one of the frequency bins when I take the Fourier transform. Okay. And if my signal has to lie on a bin, my discrete time frequency must be of this form. That is, it should be of the form m times the bin width. At an integer multiple of my frequency bin is what my discrete time frequency should be. So what will be the corresponding continuous time frequency then? Assume that the sampling rate is fs. M by n times? See, remember, when I sample, a frequency fs maps to 2 pi in discrete time. When I sample, the spectrum in continuous time repeats with fs. In discrete time, the spectrum repeats with 2 pi. So 2 pi maps to fs, or fs maps to 2 pi. So if this is fs, this guy is m by n times fs. Simple. I mean, something you should remember, 2 pi is basically fs when you sample at fs. So this is how we should choose your sinusoid to be if you want the signal to fall on a bin. Clear? So I went ahead and made sure if this is the case, that's what you should also do. Just because I say something in class, don't trust me. Have that scientific temperament of, go and checking yourself. Sorry.
How we wrote that n minus 1 into 2 pi?
This one?
Yes.
This is okay. 2 pi minus omega naught is the thing. Omega naught is this.
M into 2 pi.
That's all. That is basically n minus m times 2 pi by.
Okay.
Actually, again say, right? I mean, see, right? Omega naught is m in the frequency bin. 2 pi is n. So this is n minus m. I mean, however you want to remember, you can do. So I went ahead and made sure this is indeed the case. So I've taken an example where I chose the sinusoid of this form, 2 pi into 201 by 1024 n, and I took a 1024 point DFT. So the x-axis is basically k. K spans till 1023, 0 to 1023, and as you expect, you see two peaks, one at 201, other at 1024 minus 201. You subtract 4 in hand, 4 in the mind, 1 in the finger, whatever, and then you get 823. Again, I just want to highlight that these are all discrete points actually. I've basically joined all to look like a continuous plot, but these are all actually individual points, from 0, 1, 2, 3 and so on.
So this is plot for signal line on mid, right?
Correct.
But like it should be 0, but minus 250 on the right.
Sorry, this is in decibels. Okay, I probably should clarify. This is in dB. So whatever you get as the Fourier transform, you take 20 log to the base 10.
Yeah, it means it was very small.
Yeah, minus 250 dB is virtually 0. That's basically 10 power minus 12.5. This is basically the precision of the computer, literally. Anyways, so this is the case. So now let's look at a case where signal is not of this form, right? Because there are only two possibilities. One, it is like this, or it is not. Let's also see what happens in the other case. So here I have chosen my signal. Let's take an example. Let us say I choose my omega naught so that it is something like 201.1 by 1024. It is not like of the form m by n, where m is an integer. Okay, I mean that is also, this is what I want, but I am choosing it otherwise. So let's quickly look at these values. Oops. So now what will be the value of omega naught here? What is omega naught? This is what I have chosen. What will be the null frequency? 2 pi into, I mean omega naught is 201.1. So this is 1 2 pi by n away. So what will be this frequency? Okay. Similarly, this will be 200.1. Okay. So again, other side, let's not worry about it now. So here again, I am going to take the samples at the same frequency points. Nothing changes. K times 2 pi by n, which is K times 2 pi by 1024. So where will I sample here now? Will I sample at the middle? You will sample slightly to the left. So the next sample to the right will no longer be at the null exactly, slightly to the left. So everywhere I will be sampling slightly to the left, right? So you no longer get one impulse, instead you get a skirt like this, right? So if I look at the discrete thing, I'll have something here, something here, something here like this. So this is something you obviously don't want, and this is often called as spectral leakage or DFT or FFT leakage. So if I did that experiment again to verify if what we expect is what happens. So here I am showing two spectrums. One is the old one where I have chosen the input to be of this form. Blue is the one I have chosen the input to be of this form. And as you see now, you see a huge skirt around your tone. So basically, if you don't know anything about DFT and you end up choosing a wrong frequency, you might misinterpret that you have a lot of noise here. For all that you know, you might have designed an excellent ADC or excellent circuit which has virtually zero noise. But because when you are testing your circuit, you are using an inappropriate frequency, it looks like you have a lot of noise. Okay? Yeah, everything is individual points. It's like this. In MATLAB, I just connected them directly. Okay. So bottom line, when you are testing your circuit, it is always important to make sure signal falls on a bin, that is your sinusoid falls on a bin, which means the discrete time frequency must be a multiple of your FFT bin width, DFT bin width, right? So bin width is 2 pi by n for an n-point DFT. So you choose your input frequency to be of this form, which means if I am sampling at Fs, what should the continuous time frequency be looking like? What should be the continuous time frequency?
My is 2x.
M by n times. Okay. And remember 2 pi is fs, the rest is all linear scaling. So this is how we should choose. Okay. So, and this is very straightforward to ensure in simulation. When you are simulating, you can feed in any value you want in the world. You basically feed in like this. So let us say you decide like this, 201 by 1024, say fs is 10 megahertz for example. So you can feed it like this. One thing is, when you are feeding this frequency, don't find this number, say I don't know, this will be what, some 2 point, let us say 05123 megahertz something. You don't compute this, round it off to 2 decimal places and feed it. That destroys the entire purpose, right? So never compute this yourself. You feed it as a whole fraction to the simulator and let the simulator compute it to the fullest accuracy it has, right? So basically feed this as such, especially in simulator, which is something you can do. Okay. But this is nice when you are simulating in computer, but if you are actually going and measuring it, let us say the frequency turns out to be like this, 2.05123476 something. You obviously cannot feed in a sinusoid with this much precision. You will have practical limitations. So although you want the frequency to fall on a bin, because of the practical limitations, it might end up with a case that it is actually not, right? So for example, let us say the frequency is like this now. Just giving an example. Or it could be 001, anything. So in that case, again, you'll end up with the same skirt. So again, this is basically, I've chosen, I think, 201.01 by 1024. This is not because you didn't know about DFT, you know everything. You wanted this frequency to be like this, but because you cannot generate frequencies with infinite precision, you end up with a case.